So I wanted to start off with a reminder of what we've been doing, okay, and that is that we're, as of right now, we're using geometry ideas to find the area, and we're doing this with linear equations, and this is just one of the problems in the book. It's number 20 here. And what we're saying here, and what we're trying to do, is come up with a function that can evaluate the area under our line, and so that's just the blue area. And so this one is a trapezoid, and so when we think about geometry, we're just going to use the formula for the area of a trapezoid, right, which is 1/2 times the bases times the height. Okay, and remember that our height is kind of back, it's kind of upside down here. We're using this as our height, and these here, the vertical part, is our bases. And so then we're just going to fill this in. And again, this should all make sense to you guys. So then our area function is 1/2. Our first base is f of 0. Our second base is f of x, and that should look right from the picture. And then our height is actually going to be x minus a, whatever our a is. And so in this case, this is a nice easy one, right? Our a is 0. So as I fill some more of this in, f of 0 is 5 plus our f of x is going to be 2x plus 5, right? That's going to depend on where we stop, and that's why this is just a function for any, that's going to give us any area under this curve, or this straight line. And then x minus 0 is just x, and so then we have that. So then when we simplify this down, we're going to have x over 2 times 2x plus 10. Sorry, the pen I'm using isn't as good as I'm used to. Come on. And then so then finally what we're going to have is x squared plus 5x. Okay, and so this is our area function that we've created. So remember, what we just found is, this area function is going to give us the area under our original f of x at any x value. So all we can do, this is just a function, so we're just going to be able to plug in a number and get something out. And that something out is going to give us that exact area for the x value that we're checking. So the other thing that we've been thinking about is how this limit ends up working, okay? And so, for our example above, it was really easy, right? It was just a linear function, and so we were able to use the idea of trapezoids, and then, on different linear functions, we could just use triangles depending on where you're starting. But, remember what we were doing over here. We had this statement over here that was saying, if we sum up everything, every height, and then multiplied that by the width on this interval, we would get the area function also. And what we were doing here was saying, as we make our width smaller and smaller and smaller, so that was almost nothing, and then we took every single height along our x-axis and multiplied these together, and then added them up an infinite amount of time, we would get the exact area underneath. Okay, and so this was going to work for any of our curves. Okay, so we have these two things that we've been talking about, and now we're going to think about what they're calling the fundamental theorem of calculus here, and how these things kind of come together. The other thing that we're talking about is when we had our area function, and in our example we have this, we talked about like, hey look, if we took the derivative of this, what would we get? And so when we took the derivative of our area function, we had 2x plus 5, and that was what our original f of x was. And so we were saying, oh, look, there's a connection between the two. And so I guess that's the third thing that you want to keep in mind is what we're talking about, or for what we're talking about here in this next part. All right, so this is just out of your book, and I'm going to kind of talk about things that should make a lot of sense while you're looking at it. Right now, instead of a linear function, we're going to have any curve here. And I think you're okay with saying, oh, okay, so if our function is from a to x, we could also be a little bit further here. And so we could call that x plus h. And so then the area of this function, and we could find it like either of the ways that we just talked about, mostly I guess with the limit. But I think you could say, okay, so this area function would be whatever, depends on what our width is down here. We would plug it in and get the shaded area here. And if we also if we like zoom in and look at just from a to x and ignore the little bit more, that would be represented by this. And then I think you'd be fine with saying if we subtracted the two, we'd be left with what is going on in this picture. And again, this is just out of your book, and I'm just kind of trying to talk through it here with you. And this area that would be left over, if h was super, super small, would just be a rectangle. And we've talked about that idea before, is zooming in would make it so that these are basically just little rectangles. Or I guess even little trapezoids if you wanted. And so then up here we're saying, like, look, if we took away these two shaded areas, we'd be left with this area that would be h times whatever f of x was. And so I'm going to just write that down here. It's just exactly the same thing as what they have up at the top. And then I'm going to talk through what they're doing in the book there. Okay, so we have this statement, and they're saying, look, what if you just divided by h? Like, let's find out what f of x actually is there. So let's just divide through by h. And we would have that the area function evaluated a little bit more than x, subtract x, over h. This is approximately equivalent to f of x. And hopefully this looks like something that we've seen before. And remember what we're doing is we're trying to find super small values of h that we can use as our width, so that when we plug it into our function we can get its height at that little point, and that way we can sum up all of these areas. And so, what we're saying here is, as h gets smaller and smaller, and you have to do this to the other side as well. What is this limit going to? Now this should remind you of stuff that we did before, because this is the left-hand side of this is just the definition of a derivative. And remember, a derivative is just a slope, and so this should remind you exactly of that. And in fact, what we're saying then, since this is the derivative, we can actually change our notation a little bit and say, well, really, since this left-hand side is the definition of a derivative, we can just say, well, look, that means that the derivative of x is approximately, or I guess is exactly equal to, right, if we evaluated the right-hand side, there's no place to plug in h, so we would just have f of x. And so that's actually the first part of the fundamental theorem of calculus. Now, that's not a real proof, but I think that's something easy to follow. And so what we're saying is that these two things are extremely related. If we knew the area function of our original function, but we didn't know the original function, all we would have to do is take the derivative of that area function and we would be at our function that we're looking at. And so then also that's going to work in the opposite order as well. So earlier in this chapter we talked about that any two antiderivatives of the same function differ only by a constant. So we can introduce this other antiderivative that we're going to call f here. And we're going to say, well, we're looking at a different antiderivative of our original f, our little f up here, right? So we're talking about this one. So here's one of our antiderivatives, a, and we're going to say, well, let's just look at another antiderivative because all they do is differ by a constant. So that must be, this f must be the same as our other antiderivative plus maybe a different constant. So now let's think about what it would mean with what we have here if we evaluated this new antiderivative f at our endpoints a and b. So, what would this mean? Well, that would just be that we would be evaluating our area function at a plus c. And then if we evaluated this new antiderivative at the other endpoint b, we would have this statement here. And remember, if we are evaluating our area function here, let me get this, and this one, when we're evaluating our area function at the very first endpoint, there is no area there. So then we get to this kind of statement, 0 plus c, and so really that's just c. And if we, oops, sorry. No, that's what I meant, yeah. So if we make this move here, if we subtract our two antiderivatives evaluated at the endpoints from each other, we would have the constants would cancel, and so then we could have this statement. And so now we can tie all this stuff together, and we're saying that our area function here is equivalent to what we're saying there is this equivalent to taking all the small little intervals underneath this curve, multiplying by the heights, adding them all up. Well, that's the same as this statement. And you may be saying, yeah, okay, great, I followed along, it makes sense, whatever. But let me show you, let's take a step back and look at what the area function actually is telling us. And so, I'm just going back to something that we did earlier in this section, and this is what really made it make sense to me. We are, okay, if you remember how this worked, this was our original curve, right? And then we started finding the area underneath the curve, between the curve and the x-axis, and we added them all up. And so that's what we were saying here. But this one represents our area function. So remember, we're finding the area function here. And this is just a function. So if we wanted to know what the exact area was from A to B, we could just come down to our area function, plug in B, find the line, and in this case, we can make up some numbers, like for this to make, be a little more solid. Maybe this would be 10, And we say, well, once we're evaluating here, oops, hold on. Once we're evaluating here from A to B, what we're saying is, if we just plug in that endpoint into our area function, we found out that the area under the curve was 10. And so then maybe when we evaluated at C, right, we would plug in C, oops, and maybe that ended up being like, let's say 15. And so then we're letting this area function do all of our summation here for us, because that's what we created here, something that we can find the exact area depending on how far down we want our endpoint to go. And so when we go back to this statement here, I'm going to only write some of it here. Like when we're going back to this statement here, what we would be saying is, well, we're going to take our area function and find out what its endpoints are here. So, you know, in our example here, I guess let me change this here so that it looks more like what we're saying. Right, we weren't going from A, but what we'd be saying is, oh, what is, if you see up here, like, what is this area? Maybe that's what we want to find. Well, what we would do is say, well, we know that the area of all of from A all the way to C is 15. And then we also know, like if we're looking at the area from A to B, we know that is 10. So if we know and this goes back to what we were doing on the other slide, if we know that the full area between the two are, you know, if we had, this would be like our f of x plus h would be 15. It was a of x plus h would be 15. And our a of x was 10. We could just subtract those two. And we'd say, well, that area that I colored in up top, up here, would just be 5. So that's pretty cool. And like, so let me show you through an example what that does. And again, maybe you don't quite see it quite yet, but let me show you what that does. So you ought to recognize this problem. This was from the quiz that you guys just took. And you know, we found the exact area, and this was where we had to go through that the limit as delta approaches 0, right, as we were taking smaller and smaller intervals, finding its height, you know, plugging in this specific little x value into our function so that we could get the height on every single one of these little intervals, all infinite amount of them, and then we added them all up, okay? So what we just talked about is that, well, we can do it this way. We have this statement now. And so since we've just shown that all these things are interrelated, right? Like the antiderivative, the derivative of the antiderivative is the function. So if we go in the reverse order and say, well, let's find the antiderivative of 2x squared, right, that would be 2x cubed over 3. And let's evaluate that at 1 to 6. And so just as a side note, what you're saying is we found this antiderivative and we're going to evaluate it between these two endpoints. Then all we have to do is find this f that we were talking about, this big antiderivative, another area function, right, at these two endpoints. So then we can say, well, 2 times 6 cubed over 3 minus 2 times 1 cubed over 3. So that's 2 times 216 over 3 minus 2/3. 216 times 2, 432 over 3 minus 2/3, which is 430 over 3, which is 3. It's going to be this 143 1/3 that you guys found through doing the whole limit summation situation. So, yeah, there's the fundamental theorem of calculus at work. And so now when you are asked to find the area under a curve, then you can just take this derivative and evaluate that. I'm sorry, take this antiderivative and evaluate it at its endpoints. And then subtract them. Make sure you subtract them. And in fact, it shows you, it gives you the net area, right? The total change, and you don't have to worry about whether what intervals are above the x-axis or what are below. This takes care of that whole situation. So I'm going to do one more example, and then I think you guys should be okay. So this is just number 23 in the book, and I suggest that you try it out before you watch the rest of this, but take a pause and just kind of look through it. But all we're going to do, right, is use this idea that we did to find this area under this curve, and this is what the graph looks like on that super small interval there. So if you try it out, and then I'm going to work through it. So all we're going to do here is take the antiderivative of what we have in there, and so that's going to be, right, x cubed over 3 minus 2x squared over 2 plus 3x, and we're going to evaluate that on this interval, 0 to 1. And I'm going to simplify this just a little bit. Okay, so again, we're going to take the furthest right endpoint and evaluate it first. And so we have 1/3 minus 1 plus 3. We're going to take away 0 minus 0 plus 0. So then what we're saying is that it's 1/3 minus 3 over 3 plus 9 over 3, which is 7/3. And then they're asking us to discuss whether that makes sense or not. So 7/3 is what, 2 1/3. And my drawing isn't like super good. You can see in the book a little bit better. But if this is 1 and this is 2, then you could say, oh yeah, well there's 1 times 1, that's 1. Remember, we're trying to get to 2/3. Here's another 1. So now that we're at those 2 red areas, give us 2. And then I think you can say, yeah, okay, that looks like 1/3 more there. Okay, so pretty cool stuff. So I will talk to you guys soon.